Neutral to ground bonding is a critical aspect of electrical system safety. The primary bonding location is where the neutral connects to the ground. This connection occurs at the service entrance, which can be either at the transformer or at the first disconnecting means. This responsibility falls either to the utility company or to the property owner. Generally, the neutral and ground should be bonded at only one location in the system. This single bonding point is essential to ensure that the neutral and ground remain at the same potential, preventing circulating currents. Let's consider specific scenarios. Scenario 1 involves a padmount transformer, a meter, and a main panel board. In this case, the utility typically establishes the bond at the transformer. Additional bonding at the meter is generally not required. While bonding is often done at the main panel board, it is redundant if the transformer bond is already in place and sufficient. Scenario 2 involves a pole mount transformer, a meter with a disconnect, and a main panel board located far away. If the transformer lacks a bonding connection, then you should bond at both the meter and the main panel board. The significant distance between the meter and the main panel board can introduce impedance. This impedance may lead to voltage differences between the neutral and ground. Ideally, bonding should occur at the service entrance, whether it's the transformer or the first disconnecting means. This ensures a single bonding point. However, in practice, bonding is sometimes implemented at multiple locations. The reasons for this include redundancy, ease of maintenance, or adherence to specific code requirements. The fundamental purpose of bonding is to create a low-resistance path for fault currents to flow, ensuring safety and proper operation of overcurrent protection devices. While bonding at multiple locations might seem beneficial, it can potentially result in circulating currents and undesirable ground loops. For precise requirements and recommendations tailored to specific situations, consult local electrical codes and engage with a qualified electrician. It is important to remember that electrical codes and practices are designed to ensure safety and should be followed carefully. Always prioritize safety when working with electricity. Bonding ensures that metallic parts of an electrical system that are not intended to carry current are at the same electrical potential as the earth. This minimizes the risk of electric shock. Grounding, on the other hand, provides a path for fault current to flow back to the source, allowing overcurrent protection devices, such as circuit breakers and fuses, to operate and clear the fault. Together, bonding and grounding provide a comprehensive safety system. Now let's delve deeper into some of the technical aspects of bonding and grounding. The size of the bonding conductor is determined by the size of the service entrance conductors, as specified in the National Electrical Code, specifically Table 250.102. The bonding conductor must be large enough to safely carry the maximum fault current that could occur. Improperly sized bonding conductors can overheat and potentially cause a fire. In addition to the size of the bonding conductor, the method of connection is also important. Bonding connections must be made using approved connectors and methods such as exothermic welding, listed pressure connectors, or other approved means. These connections must be mechanically strong and provide a low-resistance path for fault current to flow. The ground rod is a common component of the grounding system. It provides a connection to the earth, helping to stabilize the voltage and provide a path for fault current to flow. Ground rods are typically made of copper or copper-clad steel and are driven into the earth to a depth of at least 8 feet. The National Electrical Code specifies the requirements for ground rods, including their size, material, and installation. In some cases, a ground ring is used instead of or in addition to ground rods. A ground ring is a continuous conductor that encircles a building or structure and is buried in the earth. Ground rings provide a more effective grounding system, especially in areas with poor soil conductivity. The National Electrical Code also addresses the bonding of metal water pipes. Metal water pipes can provide a good path to ground, but they must be properly bonded to the electrical system. This bonding helps to ensure that the water pipe is at the same electrical potential as the earth, reducing the risk of electric shock. The National Electrical Code requires that metal water pipes be bonded to the electrical system at the point where the water pipe enters the building. In addition to bonding metal water pipes, The National Electrical Code also requires the bonding of other metal parts of the building, such as metal siding, metal roofing, and metal fences. This bonding helps to ensure that all metal parts of the building are at the same electrical potential, reducing the risk of electric shock. The impedance of the grounding and bonding system is a critical factor in its effectiveness. The lower the impedance, the more effectively the system will clear fault currents. High impedance can limit the flow of fault current, potentially preventing overcurrent protection devices from operating. The National Electrical Code specifies the maximum allowable impedance for grounding and bonding systems. Regular testing of the grounding and bonding system is essential to ensure that it is functioning properly. Testing should be performed by a qualified electrician using appropriate test equipment. Testing can reveal problems such as loose connections, corroded conductors, and high impedance. Any problems found during testing should be corrected immediately. In addition to the National Electrical Code, local codes and regulations may also apply to grounding and bonding systems. It is essential to consult with local authorities to ensure that the system meets all applicable requirements. Understanding the principles of bonding and grounding is crucial for anyone working with electrical systems. Proper bonding and grounding are essential for safety and for the proper operation of electrical equipment. By following the guidelines and recommendations of the National Electrical Code and local codes, you can help to ensure a safe and reliable electrical system. Let's now consider the specific requirements for bonding and grounding in different types of electrical systems, such as residential, commercial, and industrial. In residential electrical systems, the service entrance is typically located at the main panel board. The neutral conductor is bonded to the grounding electrode conductor at the main panel board. The grounding electrode conductor is connected to a grounding electrode, such as a ground rod or a metal water pipe. The National Electrical Code specifies the requirements for the size and installation of the grounding electrode conductor and the grounding electrode. In commercial electrical systems, the service entrance may be located at a transformer or at a service disconnect switch. The neutral conductor is bonded to the grounding electrode conductor at the service entrance. The grounding electrode conductor is connected to a grounding electrode system, which may consist of multiple ground rods, a ground ring, or a combination of both. The National Electrical Code specifies the requirements for the size and installation of the grounding electrode conductor and the grounding electrode system in commercial electrical systems. In industrial electrical systems, the service entrance may be located at a substation or at a main switchgear. The neutral conductor is bonded to the grounding electrode conductor at the service entrance. The grounding electrode conductor is connected to a grounding electrode system, which may consist of multiple ground rods, a ground ring, a ground grid, or a combination of these. The National Electrical Code specifies the requirements for the size and installation of the grounding electrode conductor and the grounding electrode system in industrial electrical systems. In addition to the requirements for the service entrance, the National Electrical Code also specifies the requirements for bonding and grounding within the building. All metal enclosures, such as panel boards, junction boxes, and equipment enclosures, must be bonded together to form a continuous ground path. This bonding helps to ensure that all metal parts of the electrical system are at the same electrical potential, reducing the risk of electric shock. The National Electrical Code also specifies the requirements for grounding sensitive electronic equipment. Sensitive electronic equipment, such as computers and communication equipment, can be susceptible to damage from voltage, transients, and noise. Proper grounding can help to protect this equipment from damage. The National Electrical Code recommends the use of isolated ground receptacles for sensitive electronic equipment. Isolated ground receptacles have a separate grounding conductor that is connected directly to the grounding electrode system, bypassing the building's normal grounding system. This helps to reduce noise and voltage transients. Surge protective devices, also known as SPD, are another important component of a comprehensive grounding and bonding system. SPD are designed to protect electrical equipment from voltage surges caused by lightning strikes or other events. SPD are installed at the service entrance and at various points throughout the electrical system. The National Electrical Code specifies the requirements for the installation of SPD. Equipotential bonding is another important concept in grounding and bonding. Equipotential bonding is the practice of connecting all metal parts within a specific area to create an equipotential plane. This helps to minimize voltage differences between metal parts, reducing the risk of electric shock. Equipotential bonding is commonly used in swimming pools, spas, and other wet locations. The National Electrical Code specifies the requirements for equipotential bonding in these locations. In addition to the technical requirements for bonding and grounding, there are also some practical considerations. It is essential to use high-quality materials and workmanship when installing a grounding and bonding system. Poor quality materials and workmanship can compromise the effectiveness of the system and increase the risk of electric shock. It is also essential to maintain the grounding and bonding system properly. Regular inspections and testing can help to identify and correct problems before they become serious. Finally, it is essential to follow all applicable codes and regulations when installing and maintaining a grounding and bonding system. The National Electrical Code and local codes are designed to ensure safety and should be followed carefully. By understanding the principles of bonding and grounding and by following the applicable codes and regulations, you can help to ensure a safe and reliable electrical system. Let's discuss some common misconceptions about bonding and grounding. One common misconception is that grounding is the same as bonding. Grounding and bonding are related, but they are not the same thing. Grounding provides a path for fault current to flow back to the source, while bonding connects metal parts to create an equipotential plane. Another common misconception is that a ground rod is all that is needed for a proper grounding system. A ground rod is an important component of a grounding system, but it is not sufficient by itself. A complete grounding system also includes grounding electrode conductor, bonding conductors, and other components. Another common misconception is that it is okay to use the neutral conductor as a grounding conductor. The neutral conductor should never be used as a grounding conductor. The neutral conductor is intended to carry normal load current, while the grounding conductor is intended to carry fault current. Using the neutral conductor as a grounding conductor can create a dangerous situation. Another common misconception is that it is okay to bond the neutral and ground conductors at multiple locations. The neutral and ground conductors should only be bonded at one location, typically at the service entrance. Bonding the neutral and ground conductors at multiple locations can create circulating currents and other problems. Another common misconception is that surge protective devices, SPDs, are not necessary if you have a good grounding system. SPD can help to protect electrical equipment from voltage surges, even if you have a good grounding system. SPD are an important component of a comprehensive electrical protection system. Another common misconception is that you don't need to worry about bonding and grounding if you are only working with low voltage circuits. Bonding and grounding are important for all electrical systems, regardless of the voltage level. Even low voltage circuits can be dangerous if they are not properly bonded and grounded. Another common misconception is that you can rely on the electrical inspector to catch any problems with your bonding and grounding system. While electrical inspectors are trained to identify code violations, they cannot catch every problem. It is your responsibility to ensure that your bonding and grounding system is properly installed and maintained. Finally, another common misconception is that you don't need to consult with a qualified electrician if you are comfortable working with electrical systems. Working with electrical systems can be dangerous, and it is always best to consult with a qualified electrician if you have any questions or concerns. A qualified electrician can help you to ensure that your electrical system is safe and reliable. Now let's discuss some advanced topics in bonding and grounding. One advanced topic is the use of impedance grounding systems. Impedance grounding systems use a resistor or reactor to limit the amount of fault current that can flow to ground. This can help to reduce the risk of damage to equipment and personnel in the event of a ground fault. Another advanced topic is the use of high-resistance grounding systems. High-resistance grounding systems use a high-value resistor to limit the amount of fault current that can flow to ground. This can help to improve the reliability of the electrical system and reduce the risk of nuisance tripping of circuit breakers. Another advanced topic is the use of solid-state grounding systems. Solid-state grounding systems use electronic components to control the flow of fault current to ground. This can provide a more precise and reliable method of grounding. Another advanced topic is the use of active harmonic filters. Active harmonic filters are used to reduce the amount of harmonic distortion in the electrical system. Harmonic distortion can cause problems with equipment and can increase the risk of overheating. Another advanced topic is the use of power quality monitoring equipment. Power quality monitoring equipment is used to monitor the quality of the electrical power. This can help to identify and correct problems with the electrical system. Finally, another advanced topic is the use of predictive maintenance techniques. Predictive maintenance techniques are used to predict when equipment is likely to fail. This can help to prevent equipment failures and reduce downtime. By understanding these advanced topics, you can improve the performance and reliability of your electrical system. Remember to always consult with a qualified electrician before working on any electrical system.